Hey AP, in this video we're going to talk about Ksp and molar solubility. So Ksp is the molar solubility product. This is the product of the equilibrium concentrations of the ions raised to their stoichiometric coefficients. So we're going to look at how things dissolve and what ions are in the solution and their concentrations when something dissolves. And that's why we have ions raised to their coefficients. So usually something starts as a solid and then is going to dissolve into two aqueous sets of ions. And so remember, we can have aqueous solutions in our KEQ equations, but we can't have solids. So we're going to end up with these two multiplied together, and then depending upon their ratio, some might be squared or cubed, depending upon what we have. So remember that all group one ionic compounds are soluble, along with anything that starts with sodium, potassium. Those are both in group 1. Nitrates, and then ammonia, NH4, right, is another one of our ionic salts that are soluble. Everything else we consider insoluble in solution. However, in reality, all ionic compounds, because of their ionic, and so when they react with water, when they're in water, right, the water can come and attack the ionic compound and pull it apart because of those interactions, those ionic dipole interactions. So everything does dissolve to some degree, and we'll see that with different Ksp values. Okay, so the smaller the Ksp value, the less the compound dissolves. So the bigger the Ksp value, the more soluble a compound is. So we talk about things in terms of their molar solubility. So the moles of a solute that are dissolved in 1 liter to make a saturated solution. And just remember that this is how we get this molarity of moles per liter, is really the molar solubility, how many moles have been dissolved in that saturated solution. So solubility depends on a few different parts of thermochemistry, and we'll get much more into these in 2 units. I think the next unit is acids and bases, and then we come back to thermochem again. And there's some different terms. So we've talked a lot about enthalpy, which is delta H, which is the energy of the reaction. The other way we can describe things is with entropy, which is the disorder of our reaction. And then these two combined can help us describe something in terms of the Gibbs free energy of a reaction. And that, by looking at the delta G value of something, can tell us how thermodynamically favorable that is. So if it's going to happen spontaneously, so it's just going to happen on its own, or if it has to get forced to happen. So you might see these symbols come up in some of these questions, and just know that they have to do with how likely it is for something to dissolve or something to react. But we won't get into the nitty-gritty of those until we get to, I think it's our last unit of AP Chem. So, but we should know that the cumulative effect of enthalpy and entropy, enthalpy being delta H, entropy being delta S, determine the value of Gibbs free energy, which is delta G, and the thermodynamic favorability of dissolving. So how likely it is to dissolve depends on how much energy is required and how much disorder do we have. We like to have disorder in our solutions. So with that said, let's go through a couple example questions. So first, we want to write the molar solubility Ksp equation for the solubility of silver chloride. So silver chloride, AgCl, is going to start as a solid, and we draw our double arrow. That turns into our ions of silver plus 1, aqueous, and chloride minus 1, aqueous. So to write our Ksp, right, Ksp equals, and it's still products over reactants raised to their coefficients. So in this case, brackets around my silver, brackets around my chloride, and then silver chloride is a solid, so we don't include it. So this is our Ksp equation. Well, what if we're asked to calculate Ksp by given molar solubility? At a certain temperature, we're told the molar solubility of our salt, MX solid, is found to be 4.15 times 10 to the negative 6 molarity. We're asked to calculate the Ksp. So this means that for both of ours to dissolve, we know that this dissolves and has a concentration So if this is my reaction, my solid dissolves into my two aqueous ions. I have a concentration of one of my ions to be 4.1 times 10 to the negative 6 molar, and the other one is 4.15 times 10 to the negative 6 molar. So that's what this tells me, is that at equilibrium, this dissolves to be this concentration of both of those. Well, Ksp is equal to the concentration of our ions multiplied together. So we're just going to plug those in. 4.15 times 10 to the negative 6 times 4.15 times 10 to the negative 6. And when we do that, we get 1.72 times 10 to the negative 11. And we don't have units on our Ksp. Okay, so we can see that this is a pretty small number, so it's probably not very soluble. And we could compare that with another one. Well, what if we're given concentrations of two solutions, and then we're asked to figure out, well, does this dissolve or does it not dissolve? Do we get a precipitate? Do we not get a precipitate? Wow, that really zoomed in there. All right, so we want to predict the formation of precipitates if 150 milliliters of a 0.00395 molar barium chloride and 550 mils of a 0.00775 molar potassium sulfate are mixed, will a precipitate form? So we're trying to figure out, does us putting barium chloride with potassium sulfate, do we get barium sulfate solid out, and our other item would be KCl. So we're trying to figure out, does this happen? Well, we're told that the Ksp is 1.1 times 10 to the negative 10. So I need to know, well, for this to happen, for us to make the solid, barium sulfate as a solid would be coming from the ions of barium plus 2 and sulfate minus 2. So we need to figure out, well, what are our initial concentrations? What are we looking at? Because we need to look at our Q to see, well, what do we actually have? And then we need to compare our Q to the K to see, well, am I going to make this? Yes, or no, am I not going to make that? So let's take a look. First, we need to figure out, well, how many moles do we have of each of our solutions? So if I have 0.150 liters of my barium chloride, so that is for every 1 liter, 0.00395 moles BaCl2. I get 5.925 times 10 to the negative 4 moles of BaCl2, and there's 1 mole of barium plus 2 ions for every, oops, I wrote that wrong. For every 1 mole of barium chloride, there's 1 mole of barium plus 2 ions, right? There's 1 barium for every barium chloride. So that means times 1 divided by 1 means I have 5.925 times 10 to the negative 4 moles of barium plus 2 ions floating around in my solution. For my other one, I want to look at how much sulfate I have. So 0.550 liters. My concentration of that for every 1 liter, 0.00775 moles potassium sulfate. And I can just do my next one right away. For every 1 mole of potassium sulfate, I have 1 mole of sulfate ions. So when I do that, I get 0.00426 moles of sulfate ions. So now I know my moles of barium ions floating around and my moles of sulfate ions floating around. So for barium sulfate, its molar solubility into barium ions and sulfate ions. We said that the Ksp for this is 1 times 10 to the negative 10. Well, my initial conditions is that I have 5.925 times 10 to the negative 4 molar. Well, this is in, let's see, what is my solution? 150 and 550 mils. So I have this many moles of this guy. And in terms of concentration, if it's in solution together, that means that I have 150 mils plus 550, so 600, 700. So by 0.7 liters. And for my sulfate, 0.00426 moles per 0.7 liters. So -4. Just doing this calculation. So 8.46 times 10 to negative 4 molar for my barium, and for my sulfate, 0.00609 molar. So remember, Q, because these are not at equilibrium, is same formula. So barium plus 2 by sulfate minus 2. So 8.46 times 10 to the negative 4. And 00609. I get 5.15 times 10 to the negative 6. 0.15 is 10 to the negative 6. So if this is Q, that's Q, and this is K, I can see right now that Q is much bigger than K. Okay, so if Q is bigger than K, that means that my product concentration is too high, right? Because Q is too big. Remember, this is products over reactants. So I need to make Q smaller. So if I make the Q smaller, I need to shift it towards my reactants, which would make this guy smaller. So if my product concentration is too high, it's made this too big, that means that my reaction will shift towards the reactants. And we can see that my reactants is my barium sulfate. So if I'm shifting towards the reactants, that will shift left towards our barium sulfate solid, which is our precipitate. So, long story short, predict the formation of the precipitates. Will we have a precipitate? Yes. A precipitate, PPT, will form. All right, we'll practice that a whole bunch more tomorrow in class.